Hi there, welcome to a bonus video to part 4 of our LOGIG series. In the main video, I said several times that there are different ways of writing down the logical process we are learning. In this video, I'm going to look at a few of the different ways of doing it and try to show that when you get right down to the basics, they're still doing the same thing that we have learned, just a different way of showing it. In part 4, I introduced the syntactic rules for deriving arguments and I paired them into introduction and elimination rules. For me, this is the most straightforward naming system, but we've already seen that this can sometimes cause confusion. Other names for these rules also exist, and some of them may help you to understand better what these rules are and how to use them. I've replicated some examples here from the first page of a Google image search for natural deduction. You can follow those links, I'm sure, to find out more information on all of these different ways of writing logic. To be clear, these are the ones that I understand the least, and so there's a much higher chance of me making a mistake when describing these. So please follow up on some of the links in order to find out how to use these properly. If you do search on Google for natural deduction, you will also see two other symbols which we will skim over in this video, but which will become very important very soon. These are the backwards E symbol and the upside down A symbol. These are called quantifiers and they'll become important to us in part 6. But for today, very quickly, the backwards E symbol is called the existential quantifier, and very roughly it says that there is at least one of these things that exists. The upside down A is called the universal quantifier, and very roughly it means absolutely all of these things are a certain way. These quantifiers are needed for the next stage of logic, but you will see in the image search that they're also used in introduction and elimination rules in much the same way as the rules we've learned already. On to some of these examples, and here is a derivation that looks very familiar. It's almost exactly the same format that we have already learned. See if you can follow every rule through this proof. Also, is there something a little bit odd about this proof? Something that makes it a bit different from the examples we've seen so far? The answer will come up in part 5 when we discuss theorems. But the only major difference in this table form is that it does not record at each line which premises are supporting it. It's not absolutely vital to record this if you're using proof spines and you clearly understand how they work. Once you understand the rules, you'll probably use your own shorthand version of the derivations. We don't even have to include every line. The derivation on the right here could have an extra line after line 10 that fully states the contradiction Q and not Q before going on to negate line 7 in the next step. Here we can see exactly the same derivation but written in a slightly different way. For a start, the proof spines are now proof boxes, which makes it a bit clearer to look at, although it's probably not easy to draw these boxes the first time you go through a derivation. The other thing that's different about this derivation is the way the steps are named. The first two steps are called suppositions. We've also called these assumptions or premises, and sometimes hypotheses. I'm sorry, there's just a lot of names for these things sometimes. The next step is called simplification, which is another name for the conjunction elimination rule. We take one side of the conjunction alone, and this is simpler than the whole conjunction. Modus ponens is also quoted as a name for the conditional elimination rule, and then further down, the negation introduction rule is referred to as reductio ad absurdum, which we have seen before. And the conditional introduction is called conditionalization, or sometimes the conditional proof. One example not seen here is that the disjunction elimination is sometimes called proof by cases, because you have to prove both sides of the disjunction, both cases that could be true. So the way that we have looked at doing derivations involves working down the lines of a table. Another way of doing derivations is called truth trees, where each step of our derivations can be a branch point on a tree of possibilities. Truth trees are a useful tool because it lets you explore several different directions of the derivation at the same time in a semi-organized branch form. The same rules that we've learned are written down in a form which means that we can work down a page in branches, ending or connecting branches when needed. The rules can be laid out to assist with this, such as with the conjunction introduction here. A is on the left, B is on the right, and we move down to the conjunction underneath. The conjunction elimination, shown here as a separate left and right version, shows us deriving A and B into A alone or B alone. We saw this called simplification in the last example, and it's similar with the disjunction introduction rule. The disjunction elimination rule is a bit more complicated. It shows that if we have A or B, and then we have two separate derivations of C from each one of them, then we can use the disjunction to justify C. The Greek letter alpha in this example shows the two branches are replaced by the disjunction at this step. Similarly, with the conditional introduction rule, a derivation from A to B allows us to introduce if A then B, not resting on A. And finally, the conditional elimination is another rule that shows two premises at the top combined into a conclusion at the bottom, this time to show modus ponens. If A then B, A therefore B. Now here are exactly the same rules again, only what the hoojuma flip is all of this, right? These really are exactly the same rules, I promise, but they're written in a much more abstract way. Don't worry if you don't want to go into this for now, you don't have to, but very quickly, let's spin through what they mean. Looking at what is labelled as the conjunction introduction rule, we can see that once again, two inputs at the top lead to a single output at the bottom, and this output includes a conjunction. Our simple statements are the lowercase Greek letters phi and psi, but we're not simply introducing them like we did before. Instead, we're saying that each one of them is implied by a larger set of premises, which is shown by the capital Greek letter gamma. So the syntax is this: if gamma implies phi and gamma implies psi, then gamma implies the conjunction of the two. The set of premises gamma is all the background assumptions that you need before any reason can begin. For example, I am in a world, that world is shown to me by my senses, etc. Of course, we don't need to refer to this set every time we think about logic, and so that's why we often use a simpler notation. But this is strictly a more accurate idea of logic representing a world. See if you can use the examples on the last slide to match our understanding to the examples on this slide. I just want to look at one more, the conjunction introduction. Here, the top line is very similar to the sequence we've learned about. If gamma and phi together imply psi, then gamma alone implies that phi implies psi. That is confusing to listen to, so do go through it on the page for yourself. But this syntax can also show us how the premise phi is removed in this rule. We conclude that only gamma is enough to imply that the conditional is true. We know that if phi is also true, then psi would be true. But it doesn't actually matter if phi is true or not. We can imply the conditional between them anyway. Finally, this picture also includes a new rule, which is how we actually introduce claims into our derivation. It's sometimes called the rule of assumption. The syntax here is, if phi is a member of the set gamma, then gamma implies phi. Being a member of a set is a piece of notation from set theory, meaning that phi is part of set gamma, and so if we have set gamma, then we automatically have phi. We have mentioned set theory before and the common link between sets and logic, but that's all we'll say about it for now. The next way of writing logic is more straightforward, and it's mostly friendly to the early typewriters that did not have access to many unusual symbols. That said, it does use this odd triangle of dots for therefore, which is not on a typewriter. The premises are on the left in a column, and then in the last line we tab over to use the slash to introduce the conclusion. Here we can see our conjunction elimination, conjunction introduction, and disjunction introduction rules written out in this very simple form. Now here in the same form we can see modus ponens again and its brother modus tollens. These are basic rules of inference that demonstrate the relations of necessary and sufficient conditions. Modus ponens shows the sufficient relation. P is a sufficient condition for Q. If you have P, then you certainly have Q. Modus tollens shows the necessary relation. Q is a necessary condition for P. If you don't have Q, you can't have P. Here are two more valid rules of inference. A syllogism is an ancient word for a valid form of argument from reason. The disjunctive syllogism makes it clear that if at least one of two things is true, and you show one to be false, then the other one must be true. P or Q, not P, therefore Q. Or the other way round. The hypothetical syllogism is the basis for one of our earlier examples, and we called it modus ponendo ponens. It's like modus ponens but extended with another conditional. In fact, I've seen a few different ways of using the name ponendo ponens, but this double conditional makes the most sense to me, but I warn you to keep your eyes open when reading about this. The constructive dilemma is a slightly more complex rule that shows if the two disjuncts of a disjunction each imply two different outcomes, then at least one of those outcomes must be true, as long as the original disjunction is. These and several other rules of inference are still fairly easy to explain in a few words, although they may still take some work to see the logic clearly. But from here, arguments start to become more and more complex, and to correctly draw out the validity becomes harder and harder, as we shall see in part 5. In these examples, we also see a different way to show the conclusion. A colon is sometimes used in place of a syntactic turnstile, and a double colon shows that this conclusion is two-way. It is a corresponding biconditional, and this is a logical equivalence. There are many equivalences, an infinite number in fact, and several more can be seen on the original Google image, but we'll just look again at two that we have seen before, the double negation and De Morgan's relations. The double negative is a very simple logical equivalence. It is a single valid step to derive not P to P, and a single step back again from P to not P. De Morgan's are a little bit more complex, but in both cases you start with only what is on the left or the right, and you can derive your way to only what is on the right or the left. This is something you cannot do with modus ponens, for example, which is only one-way derivation. This is why there is something special about logical equivalences. By the way, we haven't done it yet, but in our system of notation, we can show the same thing by putting a double syntactic turnstile, one facing to the left and the other one facing to the right. So that's where we'll leave it for this video. We have not, of course, covered everything, but hopefully you get a sense of how different types of notations work and how many different styles are common. Eventually, they're all saying the same thing. They're just different ways of writing them down. And these different ways, for example, truth tables or truth trees or derivations in a table, have different benefits in testing and tracing the validity of the logic. We've not finished talking about the techniques of derivation yet though, so join us for that in part 5 of the main series. Hi, hope you found that interesting. Like, comment, subscribe, etc. If you prefer shorter videos, you can find this cut up on our other channel just up there. But whatever you do, please keep learning something, because no matter who you are or how old you are, every day really is a school day. Bye for now.